place each 3 years. Now it is already 15th conference over this tradition is for 40 years. Maybe I just copy the link to the conference in the chat, and then maybe also in the YouTube version, if it will be posted. I then will pass copy write also there some remark. But generally, this is non-conference. Unfortunately, I'm worrying because very few people have registered now. For example, last time there were 140 participants also we organized it 3 years ago, and now there are something like 20 prospective participants, so not so many.
Okay, so we will post the announcement later. Yes, so later make the record. So it's my pleasure to announce the speaker of our seminar today, Dimitri Leites. He's a famous of course, he's one of founder of the supergeometry. And today he shall speak about the how to say structure of G2 type in super setting and in positive characteristic and related curvature tensors. So please, Mitya.
Thank you very much. I'm thankful to everybody who came here to listen to me, because actually what I'm going to talk about had been published quite a long time ago, but it seems that apart from very few people, nobody bothered to read about this. So I'm using this opportunity to popularize certain ideas, some of them having, well, if not having, but at least pregnant with possible applications, namely to supergravity equations. Not to supergravity, I don't know what it is, I don't know even what gravity is, but to gravity equations. So let me start with some preliminaries. As probably every listener who came today, well, there are several names unknown to me, but I think that anyway, all of you by now know that better say superalgebras, appeared not in high energy physics after Wes and Zumina talk, or a little bit earlier in works of Goldfund and Lichtman, and also Wolf and his students, but in topology, definitely in 40s, when Whitehead proved that homotopic groups with respect to Whitehead multiplication constitute a Lie superring. And actually, these Lie superrings appeared either over integers or over finite fields. Bachstein, Meir Felixovich Bachstein, and well, people more famous than he, like Alexandrov, Hopf, Ureson, they dealt with residue field modulo 2, 3, things like that. But at that time, these Lie superalgebras were called graded Lie algebras. although they are not Lie algebras, they are superalgebras, and therefore commutational relations are different. They use -1 to some power, whereas for graded Lie algebras, we don't need this when we define commutator. And nobody bothered to study them deeply because those Lie superrings that did appear in topology, they were, let me, forgive me for a rude word, I'll say ugly from the point of view of many mathematicians, because they are just nilpotent or solvable, and therefore not much structure, not that interesting to study as simple Lie algebras or simple Lie superalgebras are. Situation changed completely between 74 and let's say 86, because first, very impressive was classification performed by many people, but skillfully rounded up by Katz and published in Communications Mathematical Physics, and with several rather reckless statements in advances. It was very impressive, still is. And it drew attention not only of physicists, but of mathematicians, and mathematicians started to study Lie superalgebras and their representations in over complex numbers and real numbers and characteristic 0. But Lie superalgebras and modular, that means over fields of positive characteristic, Lie algebras were, and still are, to an extent, kind of neglected until Drinfeld, well, I should mention, of course, Kulish and Reshetikhin and also Zhenya Sklenin as the first people who, well, who gave first examples of quantum groups, but the theory as such is, of course, due to Drinfeld. And he also was the first to understand that representations of certain quantum groups considered in characteristic 0, but for the parameter q equal to the pth root of unity, where p is a prime number, resemble very much the representations of modular Lie algebra or superalgebra over fields of characteristic p. This was further investigated by Lustig and Pavel Itingov, whom Drinfeld once appointed as, I mean, he referred to about Itingov as the person who is my representative concerning quantum groups in the second millennium. That's how he formulated this. So for many years to come. And all this has somehow to do with supergravity equations. Let me explain how. As a matter of fact, Cartan and Killing, when they classified Lie algebras, simple Lie algebras over complex numbers, they did not know about Dynkin diagrams, which are improvements of Coxeter diagrams by certain labels. As Lustig recently recalled, Coxeter, when he heard about Dynkin diagrams, tried to hint to the audience that he introduced them earlier and independently. But Cartan and Killing didn't know about this because by that time Dynkin either hadn't been born yet or was very young. Anyway, there were no Dynkin diagrams, and Dynkin's contribution to this science was in understanding the importance of root systems and simple roots. By the way, I do not see among the audience Rafael Stikolchik. Probably I forgot to send him an invitation. He lately advocates that one should look not only at the Cartan matrices and basis of simple roots, but also certain partial Cartan matrices. So this is something that I would like to tell everybody. Pay heed to Stikolchik's latest papers.
Can I ask a question?
Yes.
The question is, so after this classification that introduced the simple objects in super Lie theory, did anyone, are there any examples known from topology? Like, are there any homology theories with a simple Lie algebra?
Excuse me, John, you mean of simple algebras?
Yeah, of simple Lie superalgebras, for example.
I don't know. Sorry, yes. I don't know, but I knew. People, if you're interested in this, please remind me after the talk. There was, well, I'll try to make it brief because anyway, I cannot say much about this. There was one paper which I refereed for Math Reviews, and there, out of the blue, from certain constructions of Riemannian geometry that I don't remember anything about, certain simple Lie superalgebras appear. But at the moment, I don't remember who was that and something. But if you look at Math Reviews and find those reviews that I referred, there is a possibility to find this, right? You will definitely find this. I didn't refer many papers, so it will be easy to find. But apart from this, no, I don't know any simple Lie superalgebras or even Lie algebras that somehow appear from well, homotopy or homology. Well, yes, there is one example. It's our paper with Ilya Shereshevsky and Alexei Lebedev, where we consider a certain Lie algebra or superalgebra structure on the co-chains with the joint module of any Lie algebra. There, certainly algebra appears. But okay, sorry. Let me go back to main stuff. So, how did Cartan and Killing classify simple Lie algebras? They described them in terms of non-integrable distributions that these algebras preserve. And this is natural for a certain grading of, let's say, symplectic Lie algebras, and we have a contact grading in it of depth 2 from -2 to 2 with one-dimensional spaces in degrees -2 and 2. But they consider, they, I mean Cartan and Killing, considered this approach even for SLM. Right now, I regret very much that Le Hongwan and me were at Max Planck Institute for Mathematics in Leipzig. I did not read as much as I could from collected works of Cartan, which are in small but very good library there. Now, let me show you something before I start showing you something on paper. Let me say something. In 70s, Alexander Goncharov, student of Dynkin, considered certain classical Hermitian spaces and tried to solve the problem formulated by Dynkin, how to figure out something global from the local structure on these spaces. These spaces admit, well, the group of symmetry of these spaces is a complex Lie group whose Lie algebra is graded of depth 3. Simple Lie algebra with grading of depth 3 from -1 to 1. And it was from the PhD of Goncharov that I first learned that the Riemannian tensor can be described as a certain cohomology, because in the courses of differential geometry, I learned that it's some tensor with some indices here and there in these analytical terms, which I was and still am absolutely unable to understand. But it can be described like this. We have this simple Lie algebra. Now, on the -1st space, the 0th component acts preserving a certain tensor. For example, suppose here is orthogonal group, and this is just its tautological module. Well, if we add to this orthogonal, I said group Lie algebra, of course, to this Lie algebra center, then it's possible to add something, and the whole group of automorphisms of this tensor becomes bigger. It's not like this, but like this. Okay. At that time, I learned also that if you take any simple finite-dimensional Lie algebra and its grading like this, not every simple finite-dimensional Lie algebra can be graded like this, but let's consider those that can. Then, if we try to extend this, what's called Cartan prolongation, if we try to construct this prolongation, it is actually a very simple thing. We have minus first component, and we have zeroth component that acts on it. We realize the zeroth component as linear vector fields, minus first component is spanned by partial derivatives, and then this pair is embedded into vector fields with respect to the standard grading. The degree of every indeterminate is equal to 1. And then the first component consists of vector fields of degree 1, such that the bracket with minus first component lies in the zeroth component. This gives us the first component. Then the second component is defined in the same way, and by induction, this way we construct the whole what is called Cartan prolongations, the direct sum of those prolongations. Abstract definition of this given here is actually very seldom needed, if ever. This is probably one of the reasons, by the way, why constructions by Cantor, who considered Cartan prolongations in an abstract way, did not draw as much attention as it probably deserves. Okay, now, if you take any finite dimensional simple algebra graded like this, then and take its non-positive part and try to extend it to the positive part, you will find out that it is possible only in two cases. I mean, if in general, if you take simple finite dimensional algebra, take its non-positive part, take its Cartan prolongation, the outcome will be the same linear algebra you started from, with two exceptions. One exception is this: you have a cell, and its Cartan prolongation is divergence-free vector fields. Another exception is different. It is not of degree, actually, it's not graded like this. It's graded from -2 to 2. And the result of somewhat more general construction of this Cartan prolongation gives the Lie algebra of contact vector fields. On the tangent space to the contact manifold, there is a structure of the Heisenberg-Lie algebra, or in other words, there is a codimension 1 distribution. I added to some of these 3 papers that I asked Van to send to the participants to look at home and quietness, several references which were absent there at the beginning. For example, I added a reference to the paper by Vershik and Vershkovich, where they prove that if we consider a non-harmonic, non-integrable distribution and consider the Lie algebra that of its symmetries, then we have only 2 cases. One case is of distributions of codimension 1, and this is contact distribution, and the algebra is contact algebra. It is simple. The second case is so-called angle distribution to dimensional subspaces in 4-dimensional space. The algebra of symmetries of angle transformations is not simple. And from that time, when I asked Goncharov why he considers only gradings from -1, from -1 to something. What will happen if we consider gradings of the depth d, from -d to d, which is applicable to any simple finite dimensional algebra. At first, I couldn't understand this, and then there was another problem that bothered me. I have encountered the following formulation of Darboux theorem. If we have a symplectic manifold, then the non-degenerate symplectic, non-degenerate closed two form on it can be reduced to the normal shape dp dq. I just couldn't understand why it differs so much from the formulation in the Riemannian geometry. Look, when we are talking about a space, just a space, and a non-degenerate, let's say, symmetric form on it, we can reduce it to a certain normal shape, let's say, over an algebraically closed field. And the same in the symmetric case. But here we have manifold, and at every point, in the tangent space at every point, we have either metric or simple non-degenerate antisymmetric two form. Why? For one, abstractions to integrability, to reducing to the normal shape, constitute a Riemannian tensor, and in the second case, there are no abstractions at all. Well, it took me several years to understand that classics of differential geometry never formulated the theorem like this. They formulated it correctly, namely, non-degenerate differential two form can be reduced to the normal shape if its differential vanishes. So we have absolutely parallel description in the Riemannian and in the symplectic case. So Riemannian case is the case of almost flat. If the Riemannian tensor vanishes, then the metric can be reduced to the normal shape. In the almost symplectic case, when we have a non-degenerate antisymmetric form, we also cannot reduce this form to the normal shape, unless the differential of this two form is equal to 0. And then we call such a manifold symplectic. Well,
Mitya, did you wrote this observation in somewhere?
Pardon?
Did you write this observation also uniform Riemannian case and the symplectic case somewhere?
This is this paper, one of this paper precisely.
This paper, okay.
Yeah,
but you say that you did not publish it, or did you publish it?
Yes. Everything is published. Everything is published. Only one of the papers that which is called char P3, characteristic P equal to 3 with Grozman. Well, the other two, the paper by Irina Shepechkina and this one by 4 authors, they are published and they are in archive. The paper with Grozman is also published, but I've realized that it's very difficult to read it. And there are even small mistakes. Well, absolutely silly mistakes. Well, in some place it's written that there are either 2 or 3 parameters, and then the answer is given that there are 2 parameters, not 3. So anyway, you have a chance to get the corrected version. With I deliberately did not delete my comments in certain places for you to enjoy and maybe answer these questions and help me to with calculations somewhere. Okay.
Okay, thank you. Yes.
But here comes also the following. Here we come to the following question. Suppose we are wishing to compute the NYUAD tensor that distinguishes almost complex manifolds from complex manifolds. For this, we consider not complexly algebra, but real algebra, well, and compute certain cohomology. Which cohomology? We have to look at formula, yeah, formula 4 here. Yeah, here it is written, and what is written here is actually very clearly written, and therefore it's easy to understand who wrote this. Okay, now if you take the book by Shlomo Sternberg on differential geometry, you will see that he computes certain Spencer cohomology. What are they? Look at this formula. Let's go backwards. Look at this formula. G star is Cartan prolongation, so it is graded. Suppose we are taking the component of this space of degree k, I mean with values in degree k. These are precisely h2, 2 comma k, or maybe k minus 2, depends on how you norm this, Spencer cohomology. But there is no way to compute Spencer cohomology except by definition. I mean, it's quotient of the closed forms, modulo exact forms. To do this is not fun, and unless you are Lena Politaeva, who can do it with bare hands. No, other people enjoy possibility to ask to use Grozman's package superly. Or if this Cartan prolongation is a simple algebra, then you don't have to compute at all, thanks to Bott-Barrel-Weil theorem. I mean, you just apply this theorem in one of particular cases. But when you rewrite Spencer cohomology and definition of Riemannian tensor in this way, there is just, it is remains very natural to generalize this to the case of algebra of any depth. Then you take its negative part and compute the cohomology of this negative part with coefficients in the Cartan prolongation. This way, you can compute analogs of the curvature tensor in the in presence, I mean, taking into account the non-integrable distribution. Well,
Mitya, that's very interesting because I just have recently also working on this integrability. But what is a circumscribed curvature tensor? What is different from normal curvature tensor? Yeah, your definition that's not curvature tensor but circumscribed, and that is
I called it like this because Vershik in his papers called it not it. Curvature tensor is often applied to measure curvature of a connection. In presence of a non-holonomic distribution, Vershik considered so-called truncated connection. Well, I imagined somebody with an X who just cut this connection. Well, maybe my imagination is too vivid, but I felt sorry for this connection, and I suggested to use less dramatic instruments and call this the corresponding curvature tensor not truncated but circumcised.
So that if I understand correctly, that you unify the integrability of the symplectic structure, Riemannian structure, and the complex structure in terms of the cosecant in Spencer cohomology?
Well, no. First, forget about Spencer cohomology. In one of the papers, in the paper published in Theoretical Mathematical Physics, in the collection dedicated to the memory of Ludwig Fadeev, I even wrote that, in my opinion, Spencer cohomology are appropriate for people. Let's use Lie algebra.
Lie algebra is the coefficient. That means that Lie algebra is the coefficient in G star here.
Excuse me?
That is a cohomology. It's a coefficient or relative cohomology. Your notation. That's a
well, if your algebra of symmetries of whatever you are considering in the Riemannian case or in almost complex structure is such that it admits grading from minus and above, so grading of depth 1, then it's easy to recalculate Spencer cohomology in terms of Lie algebra cohomology and backwards, except that I don't recommend anybody to recalculate Lie algebra cohomology in terms of complicated Spencer cohomology.
So that's your notation here. That means that is the coefficient in G star or that is relative cohomology. That's your notation of this. I mean, that's a G star and that is the coefficient of the cohomology.
G star is the Cartan, the result of the Cartan prolongation. It's the whole algebra. So this can be identified with the tangent space at the point of something. Now look. I want to say something interesting. What are the problems with supergravity equations?
Yes.
Well, Minkowski superspace is not as manifold. It is not a supermanifold. It is a supermanifold with a non-integrable distribution. Indeed, how does any textbook on supersymmetry and supergravity written by physicists start? We have odd generators Q and Q bar that anti-commute two translations. That means the brackets gives us translations. What does it mean? This means that in the tangent space, for four-dimensional in the simplest case, you select a subspace spanned by q's and q bars. If this tangent space were integrable, then by Frobenius theorem, the bracket would close, but it doesn't close. We have to add translations. Now, in the year 96-97, there was a special year at IS. Joseph Bernstein was invited there, and after this year, I asked him, well, what kind of scientific achievements did you get during this year? He said, well, there was one. Namely, I realized that Minkowski space is, Minkowski superspace is not a real manifold, is not a complex manifold. It's a mixture. It's a real manifold, just Minkowski space, functions on which takes values in the complex Grassmann algebra. And what does it mean? This QQ bar is endowed with a complex structure. But, before but, it's endowed with a complex structure. All right, suppose this distribution is integrable. Then what? Then I take the maximal, if it is integrable, I take the integral manifold and compute the analog of the Nienhuis tensor on it. But it is not integrable. And therefore, there is no integral submanifold or subsupermanifold or whatever. So we have to give a definition of the curvature tensor, in particular of the Nienhuis tensor, in presence of a non-integrable distribution. How does this, what has this to do with Sugar equation? Well, it's in the year 75 or something, Viktor Isakovich Agiyevsky, one of the leaders at that time and for many years later in supergravity, asked me, what do I think, how to write supergravity equations? I was baffled. I don't know what gravity equations are, so what can I say about the supergravity equations? I said, why don't you take the book by somebody modern like Shlomo Sternberg and replace every word the algebra by superalgebra and compute whatever it is advised to compute there. Because the idea was natural. I mean, if gravity equations are certain conditions on the Riemannian tensor, then supergravity equations should be certain condition on the analog of Riemannian tensor on Minkowski superspace. Agiyevsky said, no, that doesn't work. Some people did this. Well, physicists know what they want to get. In particular, well, they get some equations this way. And in particular, it is natural to expect that if you throw away everything super, everything odd, everything that depends on thetas and theta bars, then you at least get the usual gravity equations. And they didn't get it. So obviously this is wrong. And then I realized that the problem is in the following. We don't know how to define curvature tensor in presence of non-integrable distribution. Well, actually, there were people who tried to define it. There are works by Wagner, who thought that he found these equations. Wagner, when he was a young mathematician, even got some distinction, I forgot which one, either prize or something, at some conference organized in year 1937, where in Russia, sorry, in the Soviet Union, there was Schouten and somebody else. Also, there was a talk by Mandel. Nobody nowadays remembers Mandel. I don't know what's happened to him. Well, since it was the year 37, anything could have happened to him. I have found only one publication where Mandel is cited. It's in the book by Kaku, something about Kaluza-Klein equations. Mandel thought also that in order to describe electrodynamics, we have to enlarge the Minkowski space with the help of extra coordinates. These ideas that nowadays are attributed only to Kaluza and Klein, and he also cites them, of course. But the point is that in addition to Kaluza-Klein's ideas, he demands certain non-integrability of certain distribution. His paper is published in collections of talks at this conference, volumes 1 and 2 or something of the seminar of Veninoferj Kagan, later extended, continued, better say, by Rashevsky seminar. Well, the point is that this is possible to observe and compute. But when you compute this in terms of tensor with many indices everywhere, it's very easy to lose something. And that's what had been done in works by Wagner. Well, this claim is very serious, and I should be able to pinpoint the place where it had been done. Something had been missing. I have found such a place at some moment, but later on I have forgotten. And now probably I shouldn't have said what I said before I recovered this place in order to substantiate that this is a good definition and that one lacks something. Anyway, when I realized that it should be formulated like this, I asked Lena Poletaeva to compute this in the simplest case of capital N equal to 1 Minkowski, and she computed, and it was in total agreement. There were several components in total agreement with what physicists computed. And then to go to capital N equal to 2 or something to recover results of Agevetsky and his colleagues on this, one had to compute this, and this is difficult even to Lena Poletaeva. So I asked Pavel Grozman, and he started to write a code which is nowadays widely used, SuperLi, and he computed these and in particular reproduced the result with n equal to 1, and he got different results. Usually, well, when I compute something, you should better recompute this because I often make mistakes. Grozman was like Weinberg, for example. If he says this is the answer, this is the answer. You don't have to check. And so when I told him that, no, the answer is different, he became of the color of one's coat, very red in face, and started to double check and found some mistake in his code, but the answer was still the same. And so he asked me, who have more, we or they? I said they. And what do they have extra? Well, there was a certain condition which they, I mean everybody. In particular, we compared with one of numerous papers by Albert Salomon Schwarz. And Grozman said, well, yes, this is indeed cochain, but its co-cycle. Its cohomology class is 0. So it is like in the usual, I mean, non-super differential geometry, if you consider connection, flat connection, but you take, if you're not careful and you take some stupid coordinates, you may have some curvature, but this curvature vanishes by a more reasonable change of coordinates. So we both were very happy because we realized that we are on the right track. This is how the supergravity, sorry, not supergravity. This is how the Riemannian tensor should be computed. Now, what has this to do with G2-like structures? Well, if we take, if we take G2 and consider its grading of depth 3, that means we have two simple roots in G2. If we say that one of them, of the corresponding root vectors, one of them is of degree, pair of root vectors, one of them is of degree plus minus 1, and the other is of degree 0, then we get grading of depth 2. But if we do this with another simple root, we get depth 3. And well, this is Yamaguchi's theorem that says that you will get back, after Cartan prolongation, you will get back what you have started with several exceptions that some of them I mentioned. Now, if we take this grading of depth 3 of G2, then in characteristic 0, it's the Cartan prolongation of this non-positive part gives us back the same algebra. This is not so in characteristic 5. In characteristic 5, we get a certain infinite dimensional algebra, which was first found by Melikyan, and therefore it is called Melikyan algebra. But it was found in a different way. Namely, he considered just vector fields in one indeterminate and with coordinate restricted so that it cannot be in raised to the power greater than p minus 1, p is equal to 5. P is the characteristic of the ground field. And let it act on functions, modular constants. This is four-dimensional space because we have constants that we factorize Q. We have x, x squared, x cubed, and x to the power 4. So it's four-dimensional space. And on this space, consider this anti-symmetric form. And let the minus second space be, well, the values, this is anti-symmetric form with values somewhere. Okay, let these values lie in the minus second space. Therefore, we get embedding of this negative part, which is just Heisenberg-Lie algebra, same as for the contact algebra. The algebra of vector fields plus center, which is grading operator, it lies here. Well, in case p is equal to 5, this Cartan prolongation is a simple algebra, subalgebra here. So this is one of the constructions. Independently of Melikyan, Misha Kuznetsov found another realization that is more easy to understand, I think, namely this one. And the Cartan prolongation of this one. Together with S.Bouarroudj, we actually, that's how our joint work started. I suggested to him, let's take the super analog of G2. There is a certain analog of G2 found by Kaplansky. Let's take it. And let's take some grading similar to this one and compute something. And we have found a new, at that time, simple Lie superalgebra, except that it was not in characteristic 5, but in characteristic 3. Well, this worked. So let's try to do the same here, except that instead of Lie algebra of all vector fields, let's take the Lie algebra of contact vector fields, also in characteristic 5. I was absolutely sure that nobody will be able to be faster than us with this, because we knew something about representations of contact algebras, contact superalgebras that didn't draw much attention. Anyway, so we performed this and got another algebra. So another construction of something similar to Melikyan algebra, super construction. Okay, having done this, it was natural to look around and see what are the strange algebras about which Strade worked on classification of simple Lie algebras in positive characteristics. Together with Prenet, he completed this classification for characteristic greater than 5. But in introduction, he gave some examples in characteristic 3 and 2. In particular, speaking about some Lie algebras in characteristic 3, he wrote that, well, Yermolayev told to somebody that there exists an algebra whose zeroth part is GL2, and minus first part is something, minus second something, minus third something, minus fourth something. Without super Lie, Strade couldn't say anything more. But since we could use this super Lie package, we have, well, we could investigate this strange algebra. But there was also a guiding idea. A guiding idea was like this. Let's do the same we did in characteristic 0, namely, take algebra with Cartan matrix. All our examples are obtained either as Cartan prolongations of non-positive parts of these algebras, or of something that Shepachkina called partial Cartan prolongations, that is the same negative part, and we delete something or from the 0th part, and maybe something from the first part of the complete prolongation. Okay, so here, what do we have in characteristic 3? Scriabin observed that one algebra missed in the paper by Weisfeller and Katz does have Cartan matrix. This algebra was found by Brown, but Brown didn't observe that this algebra has a Cartan matrix. Well, Scriabin found its Cartan matrix. Okay, let's take this Cartan matrix. Actually, we know, I think that the audience knows that in super case, if you have a simple linear superalgebra whose Cartan matrix, a simple superalgebra with Cartan matrix, and such that Cartan matrix has zeros on the diagonal, it's possible to consider what Vera Serganova called odd reflections. She used first
Dimitri, it's hard to hear you.
Yeah.
Excuse me?
It's hard to hear you, Dimitri. Are you, is the microphone covered up? Or?
Do you hear anything?
Yes. Okay. Could you, you have 10 minutes more? Can you finish?
Okay. All right. So, we take this Cartan matrix, Brown algebra, this Brown of 3 with 3 by 3 Cartan matrix found by Scriabin. It has 2 Cartan matrices because this algebra, the Cartan matrices of this algebra have zeros on the diagonal, and therefore we can consider analogs of Serganova's reflections, but we call them not odd reflections anymore. We call them just isotropic reflections, reflections in this isotropic root. Okay, take any of these matrices, take the corresponding Chevalier generators, and do the same as we did in the Lie algebra case, in the case of characteristic 0, namely, say that one pair of generators are of degree plus minus 1 and the other are of degree 0. Take the non-positive part and consider Cartan prolongation. This way, we get all previously found by Scriabin exceptional algebras. He found them just because he's a genius. And we just by, well, as a result of simple calculations, And also we have found realization of that mysterious algebra that Strade writes about in introduction of the first volume of his 3-volume affair. And this gives us hope how to proceed in future. I mean, how to formulate the conjecture, let's say in characteristic 3, let's say for Lie algebras. And that is what is written in this paper. I should say that in doing so, Grozman implemented in his Super Lie an algorithm that took us, both of us, Grozman and me, several years to convince Irina Shepachkina to publish it. She thought that this is very simple, absolutely obvious, and no need to publish. Well, fortunately, we convinced her, and this is very nice paper with a very clear algorithm, which is even implemented in Super Lie. That's all I wanted to say. Thank you.
Thank you very much. Very interesting talk, Misha. I have a lot of questions, but the first question is the following things that I am interested in, because, for example, I interested in your description of the Riemann tensor curvature or anything, any condition of the non-integrability Nielsen-Heuer tensor in terms of the cosecant. But you have the diffeomorphism group action on this thing. So my question is the following: can your description give some information on the moduli space of the flat connection, or how to say anything flat? Is our diffeomorphism group action or quotient that moduli space or not?
I'm sorry. I'm sorry. One and the rest of the audience, please forgive me. I didn't understand anything.
Yeah. So I asked you that you consider, for example, flat connection.
Stop. One, please write it to me.
No. So I speak very slowly. So flat connection is how to say cosecant. So it is 0. That means that's a homology. Tensor curvature is a cosecant. So if the flat, that means that's what means a flat? That means that's not only cosecant. That is a co-boundary, or what is it? Flatnet.
Wait, if I understand you, I'm not sure that I understood you at all. I still insist, please, if you want to get some answer, please write to me.
Yeah, so that is a, say that.
Wait, right now I'll answer preliminarily. For example, when we talk about contact structure, everybody knows that it is not flat, because, well, of course, right? By definition, if it were flat, then the partial derivatives would commute, but they don't commute. Partial derivatives with respect to, I mean, these extended partial derivatives with respect to coordinates, positions, and momentum. The bracket gives us partial derivatives with respect to time, and therefore there is a curvature. But this is not this curvature that we compute by the cohomology that I showed you previously. From this cohomology theory, contact case is flat.
Yes.
And it's different. So what does it mean flat? Any
We have no Riemann form.
Yeah, there is a normal form. Any non-integral distribution of codimension 1 such that this form raised to a certain power is proportional to the volume form can be reduced in some sufficiently small neighborhood to the normal form dt minus pdq. That means it is flat, despite the fact that the traditional curvature is non-zero. So if you want to describe curvature that takes into account non-harmonicity, non-integrability, you have to compute the cohomology that I talked about.
Okay, so I should ask you another question later. So maybe ask the participant has some more question.
Yeah, I have what so a question I have is, who defined truncated connection? Was that Gontrov? Did you say that it was Gontrov who defined a truncated connection? Who defined truncated connections?
Well, I don't know who was the first. It goes back to antiquity, but well, Vershik at some moment wrote that, "Oh, I'm sorry, I did not quote Wagner." So it seems to me that probably it was Wagner.
Okay. And is that at all related, or maybe the same as what's called a partial connection?
Maybe. Well, I don't know.
Okay.
You see, well, frankly, for me, to read the papers of differential geometers written before I've realized how to talk about this in terms of cohomology is extremely difficult. And I try to avoid it.
And then it sounded to me, and I just wanted to check, it sounded to me like you were saying that thanks to calculations of Politeva, you got something like n equals 1 supergravity using these circumcised curvatures. Is that?
Well, Politeva computed this before the term had been coined.
Right.
And well, she just computed well, various analogs of Riemann and Penrose tensor. Okay. And a moment I collected her results, which she had sent to me during several years, and put them in archive. There is a longish paper, something like 70 pages, where, as a matter of fact, she uses the language of Spencer cohomology and computes them as Spencer cohomology. Because, well, despite all my bad words about Spencer cohomology, sometimes when you compute with bare hands, it's like, well, you can talk about operators in NVN form, and it's all very fine, but when you have to compute something, you have to fix a basis, take a matrix, and compute something using matrices and vectors. And, well, if you have super Lie, you don't have to do this, but if you are writing with a pencil on a page, on a paper, then, well, then I suggest you look at this archive preprint by Politeva to see how it can be done, as some say, with elan.
But is it, so does she compute these, is the upshot that she computes these circumcised curvature tensors, although not called that?
Right. Yes,
But,
she computed these without knowing that it will be called like this.
But how is it related to supergravity? How does that calculation related to supergravity, if at all? Did I misunderstand?
Right. Her calculations that I advise everybody here to look at are not related to supergravity.
Okay.
If you want to look at the supergravity, you have to, if you go to this paper, okay, you will see computations for various capital N's. We started with capital N equal to 1, then reproduced the result of Gievetsky and company, GIOS, Galperin, Ivanov, Gievetsky, Sakachov, for N equal to 2. And then we considered the case that they were unable, although physicists are remarkable people, they can do miracles, but still certain miracles are too miraculous to be performed by bare hands. And we considered the case N equal to 4 and found out, by the way, for N equal to 2, Gievetsky found out that they have to add something that they called harmonic superspace. That's in scientific terms. In blunt Nordic terms of Swedish people like Grozman and me, this is just projective space, projective line. Where do we have to add it? Let me show you. Yeah. Look, when capital N is equal to 1, then this is just a line, and this is just a column. Okay, just a row, and this is just a column. And B is 0. When N is equal to 2, well, how? Well, if we take this part, just negative part, everything under the diagonal, and compute the analog of the Minkowski space, of the Riemannian tensor, we get something, but we would like to get the usual Riemann tensor if we throw away everything super. But if N is equal to 2, we will not get it. So what to do? If here we consider not the whole B, but only part of it, John, look.
Yes.
You're looking, yeah. Look, what is Minkowski space? It's the quotient of this supergroup with this superalgebra, modulo everything which is on the diagonal and upstairs. There is something upstairs instead of zeros if we consider so-called twister picture like Yuri Ivanovich Manin did in his book. But this is too big group to factorize. In here, in B, so B is 2 by 2 matrix, all right? Let us leave just lower bottom corner. That is precisely what is needed to get the usual Minkowski space on, the usual Riemann tensor on the underlying Minkowski space. It's a miracle. Anyway, I have to to finish because, well, I can talk about this till tomorrow morning, but that would probably be a little bit too much. So let's consider the case when n is equal to 4 and 8. When n is equal to 4, here, let's do the same as we did. As we did when we considered just the usual Minkowski space. Namely, here, what is this B? B is SL4. What did Manin teach us how to consider Minkowski space? We consider the parabolic subgroup and leave just a 2 by 2 corner in this 4 by 4 matrix. So leave this 2 by 2 corner here. So we have actually two copies of Minkowski space, one initial and the one somewhere else. But that's not all. If n is equal to 8, then if we here leave a corner which is Grassmannian of 4-dimensional subspaces in 8-dimensional, I don't know how to interpret it. And also 2 corners here, everything again will be fine. But since this is not in our space, but somewhere else in the outer space, Grozman and I called them hell and paradise. And well, they are in outer space, copies of our Minkowski space. And if we consider such a picture, then everything will be fine on our Minkowski space. Now that's the complete story.
So I say that if there are no more questions, let us thank the speaker again.